Hello and welcome to DBS10012 Engineering Science. For topic 6, we will cover on temperature and heat. Are you ready? Let's go. Alright guys, so for topic 6, be prepared because we will go into 5 subtopics which are heat, temperature, 3 ways of heat transfer, specific heat capacity and latent heat, and number 5 is thermal equilibrium. Let's go. Okay, so for the first subtopic is heat. So the definition is a flow of energy that is transferred from a hot object to a cold object. And the symbol we use is Q for heat. The SI unit, we can use either calories or joule. And for heat, we have 3 ways of heat transfer, which are conduction, convection, and radiation. Temperature. The definition of temperature is a degree of hotness or coldness of a substance. The symbol we use is theta. The SI unit is K or Kelvin. And temperature is the measurement of thermal energy. Heat formula is represented by Q equals to mc delta theta, where Q is thermal energy, M is mass, C is specific heat capacity, while delta theta, what is delta theta? Delta theta is change in temperature, where final theta minus initial theta. Specific heat capacity, is the amount of heat that is needed to raise the temperature of 1 kilogram of the substance. And the SI unit we use is joule per kilogram degree Celsius, while the formula is C equals to Q divided by M delta theta. And each substance has a different specific heat capacity. For example, a plumbum, iron, water, each of these substances has different specific heat capacity.
Let's do the exercise of temperature and heat. Before we solve these questions, we list down the formula related to heat energy and thermal equilibrium. Q equal to mc delta theta and negative Q loss equal to Q gained. This question wants you to calculate the total heat energy of water. What is the formula should be used? Okay, good. List down the data that given from question 1. M equal to 0.5 kilogram. Initial temperature equal to 20 degrees Celsius. Final temperature equal to 90 degrees Celsius. And specific heat energy C equal to 4 to 100 joule per kilogram degree Celsius. Second, write the formula Q equal to mc delta theta. As you learned before, delta theta equal to final temperature minus initial temperature. Third, insert the value from the data given. Q equal to 0.5 multiply with 4200 multiply with, in bracket, 90 minus 20. So the answer is 147,000 joule. Or you can write 147 kilojoule. We go to the next question. This question wants you to calculate the mass of the liquid. So, list down the data that is given. M is variable you want to determine. Delta theta equal to final temperature minus initial temperature. Q equal to negative 10,000 joule. Negative sign indicates heat energy lost. And C equal to 140 joule per kilogram degree Celsius. Then write the formula Q equal to MC delta theta. Insert the value from the data given. Negative 10,000 equal to M multiply with 140 multiply with negative 90. M equal to negative 10,000 divided by negative 12,600. So the answer is 0.76 kilogram.
Heat capacity. Heat capacity is the amount of heat required to raise temperature by 1 degree Celsius. And the SI unit used is joule per degree Celsius, while the formula is C equals to Q divided by delta theta. Can you guys differentiate between specific heat capacity and heat capacity? You tell me the answer. Latent heat. So matter can exist in three phases, which are solid, liquid, and gas. So for example, for solid is ice, example for liquid is water, and example for gas is steam. Let me further explain it to you in the next slide. Let's go. Latent heat. Heat transfer is involved in phase changes. Okay, as you can see in the figure on my right hand side, okay, liquid can turn into solid, okay, by solidification or freezing, and solid can turn back into liquid by fusion or melting, whereas liquid can turn into gas by evaporation or boiling, and gas can turn back into liquid by condensation or condenses. Okay. Freezing and melting or solidification and fusion involves latent heat of fusion, is under that category, while boiling or evaporation and condensation or condenses is in the category of latent heat of vaporization. Okay, so from solid to liquid, liquid to gas, okay, latent heat absorbed, whereas gas to liquid and liquid to solid, latent heat is released. Okay, so what I've explained earlier is explained in this slide. Okay, freezing or solidification, melting or fusion. Okay, boiling or evaporation, and then condenses or condensation. Okay, so for latent heat, the process is reversible and there is no change in temperature. So, two situations can occur during phase change. The first one is if Q is greater than 0, the energy is absorbed. For the second situation, when Q is less than 0, then the energy is released. So latent heat is known as the amount of heat energy required to change the phase at a constant temperature. So transfer of latent heat does not cause a change in the kinetic energy of the molecules. Hence, change of phase occurs at a constant temperature, meaning the temperature doesn't change. So there are two types where latent heat of fusion is known as the heat absorbed by a melting solid. The second one is latent heat of vaporization is known as the heat absorbed during boiling. Okay, melting and boiling. Do you get it? Next, we go on to specific latent heat. So the definition. What is the definition? Specific latent heat, L, of a substance is the amount of heat required to change the phase of 1 kilogram of the substance at a constant temperature. The unit, the SI unit we use is joule per kilogram. And the formula we use is L equals to Q divided by M, where Q is the latent heat absorbed or released by the substance, while M is the mass of the substance. And for further information, at the melting point, Q equals to mLF, where LF is the heat of fusion, while at the boiling point, Q equals to mLV, where LV is the heat of vaporization. Okay guys, for your further indulgence, okay, the definition of specific latent heat of fusion, LF, is the amount of heat required to change 1 kilogram of the substance from solid to liquid phase at a constant temperature. Okay, the temperature of an object depends on the average kinetic energy of the particles of the object. So in the process of melting, the heat absorbed by the solid is used to overcome the forces of attraction between the molecules. Okay, the average kinetic energy does not increase, and therefore melting occurs at a constant temperature. So during solidification, heat is released as the particles move back into the fixed position in the regular structure. Okay, more information guys, more information. Specific latent heat of vaporization, LV. Okay, so the definition is the amount of heat required to change 1 kilogram of the substance from liquid to gas phase at a constant temperature at its boiling phase. So during vaporization, heat is absorbed by the liquid is used to overcome the forces of attraction between these molecules. And the molecules of liquid are dispersed as molecules of gas and to do work against the external atmospheric pressure as it expands into gas. Okay, so the average of kinetic energy does not increase. Therefore, vaporization occurs at a constant temperature. Can you see the similarization? So this table shows the relationship of latent heat of fusion and vaporization of the substance. You can see this table, okay? Some of the examples are helium, nitrogen, oxygen, ethyl alcohol, water, sulfur, lead, aluminum, silver, gold, and copper. Heat transfer. So there are three ways of heat transfer. So the first one is conduction. Okay, to summarize it, conduction needs solid material, and the process is from high temperature to lower temperature, and the characteristic is you need to have a medium to transfer. Okay, so the medium must be solid. The second way of heat transfer is convection. Okay, the medium for convection to occur is liquid or gases. Okay, and the process is where hot liquid or gas will lighten up and move up, and cold liquid or gases will be slightly heavier and will go down. Okay, the characteristic is in this process, both of the substance, okay, will move by itself, and it is a continuous process. So the third way of heat transfer is radiation. It doesn't need any particle or medium, okay, to be transferred. Okay, so the process is energy traveling in the form of electromagnetic waves or photons. Okay, the characteristic is transmitting waves. Okay, three ways of heat transfer. Okay guys, so to further explain what I've given to you just now, okay, let us all watch this video.
Hi, my name is Jess. Today we are going to learn about heat and three ways of heat transfer. Heat is described as the flow of energy. Heat can flow spontaneously with high temperature to an object with lower temperature. Okay, now let me show you how the heat transfer. There are three methods of heat: conduction, convection, and radiation. First, we go to the first method, which is conduction. Conduction is a heat transfer in a solid material. The vibration of molecules or atoms from warmer to cooler areas. As examples, human shakes hands. This is one of the examples of conduction. The spoon becomes hot when the hot water pours to the cup. Ouch! Now, we move on to the next method, which is convection. Convection is the movement of mass or volume of liquids and gases from warmer to cooler areas.
And it is a continuous process.
This is one of the examples of convection. For the last method, we go to the radiation. Radiation is the heat energy that is transmitted through empty space. It is because the heat energy is transmitted through electromagnetic waves. For example, light up a bonfire. This is great to keep our hands warm. As a quick recap, remember, there's three ways of heat transfer: conduction, convection, and radiation. Now, let me enjoy my radiation.
Okay, so I hope you enjoyed the heat transfer video. Okay, so next is thermal equilibrium. Thermal equilibrium. What is thermal equilibrium? So, when different parts of an isolated system at different temperature but are placed in thermal contact, heat will flow from the part of a higher temperature to the part of a lower temperature. Okay. They will exchange internal energy until their temperatures are equalized until they reach thermal equilibrium. In the thermal equilibrium process, one object will lose heat and the other will gain it. Okay. Two objects of different temperature, when placed in contact, will reach the same temperature eventually. Okay. So the equation for thermal equilibrium is heat loss equals to heat gain, where negative Q loss equals to, what is it? Feeling a bit dazed, confused? Let us enjoy another video. Thermal equilibrium. How to determine heat loss and heat gain. Let's watch it together.
Last class before final exam.
What's not to love? Last topic, thermal equilibrium. Stop. You see that? There's nothing. You just relax, bro. It's just a feeling.
So class, this is going to be our last chapter in this semester, and today I'm going to teach you about thermal equilibrium. So what is this actually? Thermal equilibrium is achieved two objects or more reach the same temperature and cease to exchange the heat energy. This thing happens when two objects or more are placed together, and the object with more heat energy will release to the object with less heat energy. The formula will be heat loss equal to heat gain, and then we change it to the symbol, and it becomes negative MC temperature change loss equal to MC temperature change gain.
So Rafi, can you determine which substance is lost or gained?
Oh my god. Where am I?
So now Rafi, are you ready? Because after this, you will determine which substance is lost or gained. Example 1 for two substances. What we have here is milk and syrup. And in this situation, we are going to pour this milk into this syrup. And this syrup as a receiver, we call it as heat gained. And then we are going to pour this milk into this syrup. And then we label it as heat loss. For example 2, we use three substances. What we have here are Milo, hot water, and also ice cubes. Alright, firstly, we pour on Milo into hot water. And then we put on ice cubes. Rafi, you get me?
Rafi.
So okay guys, to further enhance and enrich your knowledge and understanding of this topic, let us watch a few examples.
The last question is about thermal equilibrium. Thermal equilibrium occurs when two objects have different temperatures are combined together. Objects with high temperatures will transfer energy to objects with low temperatures. This process will continue until both objects reach the same temperature. We have two objects, so the formula should be used is negative Q loss equal to Q gain. Q loss is for objects with high temperatures and Q gain is for objects with low temperatures. These questions want you to determine the final temperature of the mixture. List down the data that is given to the table. Mass of the copper equal to 300 gram, convert to kilogram. Initial temperature of copper equal to 80 degrees Celsius. Specific heat capacity of copper equal to 840 joule per kilogram degree Celsius. You can refer specific heat capacity of the object from the specific heat capacity table. Mass of the water equal to 850 gram, so convert to kilogram. Initial temperature of water equal to 25 degrees Celsius. And the last one, specific heat capacity of water equal to 4200 joule per kilogram degree Celsius. Which object have the higher temperature? Copper. So, substitute the formula Q equal to mc delta theta into both sides. Insert for each data that has a value. Expand each value to find the final temperature's value. Okay, so the final temperature equal to 28.63 degrees Celsius.
So, okay guys, okay, that's it for topic 6, which is temperature and heat, which covers heat, temperature, 3 ways of heat transfer, specific heat capacity and latent heat transfer, and the last one is thermal equilibrium. So again, I wish to thank you for your utmost focus and cooperation for watching this video. Okay, until we meet again, bye.